theories and laws, okay? Models can be ideas, equations, structures, or systems that model the phenomenon in question. So we use models most often in physics to demonstrate the motion. All right, so we use models in most of the time diagram form, okay? In physics, it's really important and really helpful that you draw a diagram of what's happening, okay? Is the rock being thrown upward? Is it falling? Is it being projectile? All those types of things are important for us to visualize the motion, okay? So that's most of the time where we see a model in the physics world. Okay, laws, on the other hand, don't necessarily explain why or give reasoning, but they most of the time describe these phenomena we see in nature, okay? They are very, very, very well tested. They have pretty much been proven completely true, right? They haven't been proven false yet. How many laws does Newton have? 3. Yep, we're going to learn about all 3 of those. And those laws usually come in the form of equations. Okay, we talked about how often we'll use physics equations in here, and it is very true, a lot. Okay, most of those laws that we will study come in the form of equations. Okay, theories can most of the time serve as an explanation of the laws. So this is how basically the whole scientific method works. You guys know that. We're not going through the scientific method because you guys are seniors. Okay. All right. Let's look at measurements, taking specific measurements, taking correct measurements here, okay? We need to use and apply both accuracy and precision when measuring something, okay? When we're taking a measurement, especially in our physics trials, we want to be both accurate and precise, okay? And we're going to talk about the difference between those two things. Can someone tell me right off the bat what precision means? Yeah, Nathan.
Closeness of the grouping.
Yeah, very good. Very good. Precision means how close together your measurements are. Okay, so when you're taking measurements, if you can get them all very, very, very close together, you may have precise measurements, but you may not have accurate measurements. So precision is how close together your measurements are. Okay, so when we're looking at how precise a group of measurements are, we want to look for very little variance. Okay, we want to see numbers that look similar. We don't want to see big jumps in our numbers or big gaps. We want to see things that are very, very, very alike. Okay, or very, very close together. Little variance as possible.
Is to what's right.
Yeah, very good. Accuracy is how well these results agree with the real or actual or accepted value. Okay, so accuracy is close to actual, right? An accurate measurement is close to the actual measurement. So is there a way that we could have one without the other? Okay, you can have precision but not accuracy if you read an instrument consistently wrong, but how can you have accuracy and not precision? If one of your measurements is a fluke and it happens to be close to the real one, that gives you an accurate measurement, but your measurements are not precise. Does that make sense? You might have 10 measurements, one of them is remotely close to the real answer, but the average of your trials is nowhere near accurate, okay? So when we take measurements, we take multiple ones so that we can average them together and hopefully get our average close to our accurate value, okay, or close to our actual value, okay? That make sense? All right. Okay, so here's what we were just talking about. If you incorrectly read an instrument, but you consistently do that, you'll get precision. And if you have different people that read your instrument, so if throughout a trial you have all of your group members measure at one time, you might have fluke readings, right? Everyone reads instruments a little differently. So throughout a trial, it's important to get accuracy and precision by having the same person do all of those instrument readings. Okay. Otherwise, I might read it differently than Alex does. Okay. We might be looking at a different angle. We might be one of us reading it wrong. Whatever. Okay. So we want to make sure that the same person does all those. Okay, so let's go ahead and read through this example here. We're going to talk about who has most accurate and who has most precise. You don't have to write this down. I just want you to read through it and start looking at this data to pick out accuracy and precision. Okay, can someone tell me, or does anyone have any idea what the plus or minus 8, plus or minus 12, or plus or minus 4 means? Yeah, essentially give or take. That means their measurements ranged 4 centimeters per second squared one way and 4 centimeters per second squared the other way, okay? Or 8 one way, 8 the other way, or 12 one way and 12 the other way, okay? That's what that plus or minus means. That gives us the variance that they had in their measurements. Okay, so who can tell me who has the most, let's see if what we, oh, here's our multiple choice answers here. Okay. So raise your hand if you think A is the correct answer. B, C, or D. Very good. Very good. Okay, C is the correct answer. Ron's value is the most accurate because his overall measurement is closest to 980. And Paul has the most precise because he only had 4 centimeters per second squared variance within his measurement. So his were pretty close together, but not very close to the right one. Okay? Very good. All right, let's look at some graphing things now. We're going to do a lot of graphing in the upcoming chapters with position versus time graphs, velocity versus time graphs, things like that. So we're going to get used to, we're going to get really, really good at interpreting graphs. Okay? So let's first pick out independent and dependent variables. Okay? Sorry, this is just kind of what we're going to go through with our graphing, so you can write down these topics if you want, but we're going to look at independent, dependent. Do you know the difference between the two? Yes or no? Maybe? Sometimes? Okay, I'm going to show you a trick to remembering which one's which. We're going to look at interpreting graphs and recognizing common relationships. Okay, those are our topics we're going to go through for graphing. Okay, so when we talk about a variable, we have both independent and dependent. Okay, variables are anything that could affect our experiment. Okay, anything that could affect our experiment, we consider a variable. Okay, so the independent variable is the one that you control. Okay, you change it, you manipulate it, you have control over the independent variable in an experiment. That means the dependent variable must be something that depends on the independent variable. Okay, so the dependent variable is the one essentially that you're testing. Okay, you're trying to find out how the independent variable affects the dependent variable. Okay, so if you're looking at a group of data, if you're just looking at a chart with data, you can most of the time pick out the independent and the dependent variable based on regular intervals for one or the other. Okay, when we manipulate something, most of the time we'll put it at regular intervals. So time every second, every 5 seconds, every 10 seconds, temperature every 5 degrees, 10 degrees, whatever. Okay, we usually put them at regular intervals. If you're looking at a graph, sometimes that's more difficult to discern. Okay, which is the independent, which is the dependent. So here is our trick for seeing which one is the dependent, which is the independent. The dependent variable sits on the y-axis, just like that, and the independent variable sits on the x-axis. Okay, so you can take the axis itself and write those clues so that you remember. Okay, the dependent variable sits on the y-axis, the independent variable sits on the x-axis. Maybe I'll draw it a little bit better. Okay, so if you're having trouble deciding which might be which, independent gets put on the x-axis, y-axis is the dependent variable. Okay, that's why most of the time you see time or temperature on the x-axis. All different types of relationships. We're going to look at linear, quadratic, and nonlinear. Okay. When something has a linear relationship, that means that our slope, okay, the slope of our line is just going to be a straight line. Our line of best fit, we call, is a straight line. That means there's a very, very clear relationship between the dependent variable and the independent variable. Okay, there's a direct correlation between those two things. The equation for the slope of that line is this right here, y equals mx plus b. That should be something that we're very good at by now, right? Okay, and finding the slope of a linear line, okay, a straight linear relationship is this equation right here, rise over run, right? Delta y over delta x. So if I ask you to find the slope of a graph that has a linear relationship, you should be able to very quickly give me rise over run and give me that data. Okay? If I have a graph that looks something like this, will my slope be positive or negative? Negative, because I end up below where I started. Okay? Very good. Okay, good. So here's just an example of a linear relationship or a linear graph. You guys know how to find rise over run. We don't need to do any practice with that, do we? Give me like a solid yes or no. We're good. Okay, great. Okay, so what if it's nonlinear? Let's look at a quadratic graph here, okay? This is when one variable depends on the square of another. Okay, so a quadratic relationship when one variable depends on the square of the other. So there's our equation for that. Y equals ax squared plus bx plus c. Okay. Okay, and our last type of relationship we're going to look at is an inverse. Okay, when one variable depends on the inverse of another, what would it mean when I say inverse? Yeah, the opposite. So it would, instead of being proportional to x, it would be proportional to 1 over x. Okay, that's what we say when we mean inverse, is that reciprocal of that. Okay, and here is our equation for that, y equals a over x. And that's what each of those look like. Okay, our quadratic at the top and our inverse at the bottom. Okay, that's what those graphs look like. So you might want to sketch those in your notes beside your descriptions.